Today we're going to be using our 78-inch hydraulic tiller on a Kubota SSV 75. Out here where we're tilling today, we have soil that varies a little bit from sandy loam to clay, and we're going to try to find some areas that maybe have some rock. And we're also going to try some areas that haven't been mowed this year too, to see how it chops up the grass and the weeds that haven't been mowed. So we'll see if there's any advantage to mowing or not mowing. I wanted to start with the underside of the tiller itself. On this 78, we have 12 ranks of 4 tiller tines. So there's 48 tiller tines, so they're this shape. They're about 2.5 inches wide and a little bit over a 1/4 inch thick, made out of hardened steel. They're held in with a single bolt because on a hydraulic tiller, the tiller is actually bidirectional, so it can spin forward or it can spin backwards depending on whether or not you want to undercut or overcut, or whether or not you're driving forwards or backwards. So obviously driving backwards gives you an advantage because it wipes out your tire tracks. So if you're making a garden or a food plot or something where you don't want tire tracks, you would be tilling going backwards. Okay, so as I mentioned before, we have 48 tiller tines on here. Each rank has 4, and you can see how they're held in with a single bolt. And this is so that the tiller tine can actually swing on the arbor. That's important because the tiller tine, if you have a bidirectional tiller, the tine needs to be canted at an angle in order to cut. You can't have it just square. So if you look at like a 3-point tiller, they're rigidly bolted because they only turn one direction. But on a hydraulic tiller, they need to float. They need to go both directions. So they'll tilt one way when they're cutting this way, and they'll tilt the other direction when they're cutting the opposite direction. The arbor itself is made out of square tubing. So it's 3-inch square tubing, the full length, and that gives it a really good rigid backbone to attach everything to. And we have thick 1/4 inch plates for each of the arbor or each of the ranks where they're mounted. So the tiller tine actually rests against a solid peg, and that's what's actually holding it when it's doing work, when it's cutting. The arbor is also driven from both ends, so you can see that we have a hydraulic motor in both ends of the tiller arbor, and that's important because what you're doing is you're splitting the work between 2 motors and driving it from each end, so you're not pulling hard across the entire arbor. If you were just driving it from one end, all that torque would have to go to the opposite end through the arbor. Here we're actually able to split it, which is easier on the motors. For one thing, you can split the flow and split the work, but also the arbor can be the right size, so you don't have to make the arbor oversized, which can get in the way of actually stirring and moving the material. Each motor has its own drive hub, and it has a special design that allows the tiller arbor to float with respect to the motor and the motor shaft. What this means is that the motor shaft will have less stresses on it if there's ever bending or twisting or hard pulling from the arbor tube itself. Let's say you hit a rock or it twists and wants to bend. That motor shaft has some flexibility in this joint. And what we have on the mating surface of the tiller arbor is a thick plate with 4 holes in it that engage these 3/4 inch pegs. So that gives us just enough play in the system that you don't have to worry about alignment or overstressing the motor and the shaft seals. Each motor is American made. It's an Eaton 2000 series motor, and they're sized for the flow rate that we use here. Our 78, you can even use this on high flow skid steers. Okay, so we just completed our first run here. The area that we're tilling has a lot of clay in it, and we mowed it once this summer, but it's got a lot of vegetation on it too. There was a few small rocks, nothing major out there. I wanted to mention that we're running on this SSV 775, and it's about 21 gallons per minute on standard flow and roughly 3,300 PSI. So I'm running it on standard flow, and this is a 78-inch tiller. So it's a good workout for it, but it's handling it fine. It has plenty of pressure, so it's making good torque. You'll notice that as I'm tilling along, you have to try to meter how fast you drive, and I'm driving as fast as I can without making it stall. And sometimes you'll notice that it will stall. That's normal. You just back off and let it take off again. The soil that we're digging here, I'll show you. We've had a lot of rain this fall, so the soil here is quite wet. And this particular bit of area here, we had a lot of clay mixed in with it, so it's really sticky, and the clay is making it tough to till, because not only is it sticking to the tines, but it doesn't want to break up. So this is a fairly extreme case of hard tilling. Now, also dry clay, when it turns into rock hard clay, that can also be really hard to till, but clay in general is hard to till no matter what you're doing, whether you're disking it, plowing it, tilling it. And so the four different versions here, I wanted to explain that we were doing over-tilling and under-tilling. And over-tilling is what I say when the tines are turning the same direction as the wheels. So if I'm driving forward, the tines are turning this forward. They're pulling me into the material. Undercutting works well if you're trying to bury vegetation, or if it's maybe tougher cutting. The tines will cut from the bottom side. So undercutting is when the tines are turning the opposite direction of the wheels. So I started here, and we had I was undercutting, driving forward. So I left tracks here, and then I turned around, or I didn't turn around, but I went backwards here with it overcutting. So this was trying to push me along as I cut, so I had to kind of hold back, because if it pushed you too hard, it would stall. It would just take too big of a bite. The next pass I took here, the third pass, I was overcutting. And so the tines were turning the same direction as the wheels. Again, I was driving forward, leaving tracks, but you could kind of see that it was trying to pull me along as we went. So you kind of had to hold back on it so it didn't take too big of a bite. And then the last pass, I was undercutting, driving backwards. And for me, this is my favorite because it gives a really good finish. It's easier to control driving backwards. And I think just the look of it, because it's been chopped up from underneath, it tends to leave, in my opinion, a better finish. So on the side here, what I want to show you is that we have adjustable bolt-on skid shoes, so you can replace them if they ever wear out or break or anything. They're made out of thick 3/8" thick steel, so they're quite stout, and just simple 1/2" bolts. We have them today in the 6" position, so we're going to be digging at the maximum depth, and you can actually go beyond 6 inches depending on the soil conditions. You can kind of roll forward a little bit and actually get a little bit deeper than 6, but usually 6 inches is more than needed when you're tilling. If you're tilling a seed bed, 2 to 4 inches is usually enough for typical tilling. What we're doing here, we have a lot of vegetation on top. We haven't killed it, so it's dandelions and grass and foxtail and thistle. We're just going to dig all that in and incorporate it into the dirt, and then we're going to see what it looks like when we get done. So digging it in deeper actually makes that vegetation kind of disappear better. So the other thing I want to mention is that the hood is a single piece of rolled 7-gauge steel, and so that's important because there's no edges inside that will cause excessive wear when the tiller tines are turning and churning that abrasive material. Also, across the full length of the back here, we have a 1/4 inch plate, which is about 8 inches deep on the top and about 3 inches deep on the bottom, and it makes a closed cross section which acts like a very large steel tube. And so that's the backbone of the entire tiller, and it's tied in with these 3/8" plates on the end here. So that's what gives it the extreme strength in the structure, which is what you need when you're doing this really hard tilling. Okay, so we're going to try an experiment here. I don't remember ever trying this before, but we have some broom grass and some other thistles and stuff mixed in here. That it's kind of dry. It's early October. Stuff is getting dried out, but we've had a lot of rain here, and this soil is very, I wouldn't say saturated, but it's very wet. So I'm going to try and overcut driving forwards. So the tines will be turning the same direction as the wheels. And the reason I'm doing that is so that when we get into this tall grass, we'll be pushing it over, and the tines will come by and chop the grass off against the ground. The ground will back it up. So hopefully that minces the grass stalk into smaller bits and keeps it from plugging up and gets it kind of incorporated into the soil. So I'm going to go maybe 50 feet here and just see what happens, and then we'll talk about it when we get done. Okay, so we try to pass here. This is on standard flow, 21 gallons per minute, about 3,300 psi. We're actually tilling a portion of the grassy field here that has not been mowed this year, so there's a lot of vegetation. It was pulling really hard. I couldn't dig down to the full 6-inch depth without it really stalling, and that's partly because of the clay factor in this soil, and also that's very wet, so the soil is very sticky. You can basically make mud pies out of it. I mean, it's very sticky, so it's hard to break up, it's hard to pull through. But you can see, I mean, we were digging down here probably 3-4 inches, depending on where it's at here, and we're getting a fairly good tillage the first pass. But if you wanted it really good, you could always take a second pass now and get it totally incorporated. Myself, if you were going to plant this like for a food plot, this is probably plenty good as it is. So I'm surprised that it worked as good as it did in these conditions, considering how tough the conditions are for the soil. So we're going to try it now on high flow, which is about 30 gallons a minute, see if that makes any difference. I don't expect that it will, because we're still really relying on the pressure to do the work here. It's just going to turn a lot faster. Maybe it won't pull me ahead quite as easy because it'll be taking smaller bites, but we'll give it a try and see what happens. Okay, so we just tried a short section here on high flow just to see what would happen. So about 30 gallons a minute. On a Kubota, you can only run high flow in one direction, and it just so happened that the couplers were set up so that I couldn't overcut anymore. It was actually undercutting. And for a situation with long vegetation, I don't know that undercutting works as well, but the result right here actually looks pretty good. It actually looks better than that, maybe because it's incorporating the grass underneath better. You are getting more bites per second, so to speak, so maybe it's chopping it up better. But you do kind of push a bulge of material kind of in the front when you're undercutting. And these conditions are really the limit for any kind of tiller, and mainly because the soil is so sticky and so heavy right here and moist. So, the results, though, look really good, and I probably could have got the same result here if I was undercutting on standard flow too, but it did a good job of chopping up the vegetation. The plant fibers are all in pretty short pieces here, and the soil is well aerated now. It's nice and loose, so it'd be a really good bed for planting crop. Be sure to check back in the future. We're going to be making more videos like this, and give us a call or check out our website if you want any more information. Thank you.